an AI-generated post for your viewing pleasure. Unlocking the power of vision language models, the Idefics3 revolution. What if I told you the next generation of AI is learning to read, see, and understand the world just as we do? This isn't science fiction anymore. The latest breakthroughs in vision language models, VLMs, are pushing the boundaries of what's possible, enabling machines to tackle complex tasks with an efficacy we've never seen before. In today's video, we'll explore how Idefics3 is changing the game in AI, and why it matters in our quest for better human-AI interaction. Before we dig deeper, let's take a moment to understand what we're really discussing today. We're exploring a paper about vision language models, a cutting-edge area of artificial intelligence, and how Idefics3 significantly expands capabilities in image and text processing. In recent years, we have seen artificial intelligence make strides that seemed unimaginable just a decade ago. From self-driving cars to virtual assistants capable of holding conversations, AI technology is rapidly transforming our everyday lives. One area at the forefront of this evolution is the collaboration between vision and language, how machines can not only understand text, but also comprehend images and their relationships, leading to a more complete understanding of content. This intersection opens up exciting possibilities, particularly in areas such as document analysis, visual problem solving, and even coding based on visual cues. Today we'll be focusing on a research paper that centers around the newly developed vision language model known as Idefics3. The researchers present significant advancements in the model's ability to process and interpret documents, leveraging a mammoth dataset that is 240 times larger than previous efforts. This not only brings new capabilities to the forefront, but also sheds light on how we can improve these models moving forward, raising questions about the very foundations of how AI interprets information across modalities. Now, let's break down some key terms to ensure we're all on the same page as we discuss Idefics3 and its developments. Vision language models, VMA, are AI systems designed to understand and generate text based on visual inputs such as images and diagrams. These models process both text and images simultaneously to create connections between visual information and language, enabling complex interactions. The architecture of these models generally includes a language model, typically a powerful pre-trained neural network that generates text, and a vision encoder that extracts meaningful features from images. We'll be discussing several critical aspects of VLM development, including the architectural choices that dictate how images and text are integrated, the datasets that provide the necessary training information, and different training methods that optimize performance. Another focal point will be the Docmatics dataset, a game-changing resource developed for training Idefics3, which aims to address the limitations of previous datasets in terms of scale and variety. With these foundational concepts in mind, let's take a deeper look into the technical contributions of the paper. Now that we have a firm grasp of the overarching themes and terminology, let's jump into the specific technical contributions made by the researchers in developing Idefics3 and see what makes this model stand out from its predecessors. First, let's talk about what makes Idefics3 so special. Built on a refined architecture, this model outperforms its predecessor, Idefics2, with notable advancements in handling document understanding tasks. How did they achieve this? The researchers created Docmatics, an unprecedented dataset containing a whopping 2.4 million images and 9.5 million question-answer pairs. This massive scale is 240 times larger than previously available datasets, meaning the model has access to a wealth of diverse examples for training. However, the sheer scale of Docmatics also raises quality concerns. It's vital to consider whether the dataset adequately represents the variety of real-world documents. With sourcing primarily from a homogeneous set of documents, the risk of skewed representation looms large, potentially impacting the overall effectiveness of the model when applied to more varied, real-world scenarios. Two essential architectural approaches contribute to its efficiency: the cross-attention and self-attention methods. The cross-attention mechanism allows the model to fuse visual and textual data effectively, preserving the strengths of pre-trained models, which is vital for performance. By keeping the pre-trained language and vision models frozen during training, researchers could enhance the expressiveness of the overall system without compromising pre-existing capabilities in text tasks. However, it's important to note that the performance of these models is heavily reliant on the unmodal pre-trained backbones used. This reliance creates a scenario where understanding which architectural choices yield the best results becomes a challenge. The paper mentions that cross-attention outperforms self-attention, but without a structured evaluation of these architectural designs, the comparison remains somewhat subjective. Interestingly, the paper acknowledges this diversity of architectural designs, but fails to discuss the real-world applicability and consequences of this divergence. It's essential to establish specific performance metrics across various tasks. Otherwise, it creates ambiguity that could mislead researchers in choosing the right models for their specific applications. Moreover, the use of a well-defined multi-stage training process that adapts based on real-time feedback is a notable advantage of Idefics3. Notably, this approach has led to impressive outcomes, achieving a 13.7-point gain on the Dakafika benchmark. However, this significant gain doesn't translate to every application, and the authors should contextualize what an acceptable performance increase is across diverse user needs. Ultimately, the researchers have crafted a powerful tool, but without careful consideration of dataset biases, variety in architectural evaluation, and the need for practical applicability, we may find ourselves limited by the technology's scope. Establishing clear criteria for assessing model effectiveness not only fortifies scientific rigor, but also guides future innovations in VLM design. We've just touched on the breakthroughs introduced with Idefics3, but this research is not isolated. Let's discuss how these contributions fit within the larger research ecosystem and some of the challenges and potential future directions the field can take. The advancements made with Idefics3 don't exist in a vacuum. They're part of a much larger narrative in the AI industry. Previous models struggled with performance inconsistencies and inefficiencies, largely due to poor data quality and rigid training methodologies. But Idefics3 is different. It addresses these shortcomings by incorporating a well-defined multi-stage training process that gradually increases data complexity and resolution for training. The use of this process connects well with the idea of optimizing training regimens that adaptively enhance model parameters based on real-time feedback from the data it processes. A significant takeaway is how this model can dynamically adapt to diverse tasks. This ability to utilize varying training strategies suggests that future VLM research can benefit from collaborative efforts to create specialized datasets that can tackle specific application needs, potentially accelerating advancements in tasks such as visual reasoning and document understanding across domains. Additionally, Idefics3's improvements in document understanding showcase that with the right data and methods, we can continually refine models to meet ever-evolving user demands. However, attention must be paid to how well those metrics correlate with real-world complexities. These developments highlight the increasing importance of creating transparent, high-quality synthetic datasets, which can fill gaps in the training data and enhance model performance across a wider range of applications. Nevertheless, without clear criteria for performance evaluation, researchers may end up making uninformed decisions about model choice, ultimately hindering the advancement of the field. As we wrap up this discussion, let's bring everything together to reflect on the significance of these advancements. In conclusion, the development of Idefics3 represents a significant stride in the capabilities of vision-language models. Through careful attention to training methodologies, a focus on dataset quality, and innovative architectural decisions, the researchers have provided the field with a powerful tool that enhances how we interact with information across mediums. As we continue to unveil the potential of AI, models that can proficiently integrate visual and textual data will be crucial for solving complex real-world problems. Enthusiasts, researchers, and developers alike can gain valuable lessons from this work to inspire the next wave of innovations. Thanks for joining us today to uncover the advancements of Idefics3. If you enjoyed this video and want to keep track of the latest developments in AI, don't forget to hit that subscribe button and ring the bell for notifications. We'll see you in the next video.